Hello, everyone. Welcome to Chamberlain seminar. This is the last seminar of this academic year. I'm Mikusheva. I will be moderating today's discussion. We are happy to have Davide Viviano, who will be talking about his paper, Policy Design and Experiments with Unknown Interference. We also have two very nice panelists, Karun Adusumilli and Toru Kitagawa. So the way we will work is Davide will be speaking for about an hour. He will stop several times during his talk for questions. Generally, you can ask questions through the chat, and I ask you to send your question through the chat. When the video will stop, I will unmute you and will let you ask your question. So we're very happy to have Davide. Please, the floor is yours.
Thank you very much, everybody, for the possibility of presenting here. So I'm going to share my slides. And please interrupt me if there are any issues of any sorts. All right. Thanks, everybody, for the possibility of presenting. Today, I'm going to talk about my work on policy design in experiments with unknown interference. I very recently graduated from UC San Diego, now moving to Stanford for 1 year. So I want to start from an example, and the example is about informing farmers who are exposed to environmental disasters to increase insurance take-up. Now, this is quite relevant in economics, as oftentimes people may be over-optimistic and under-insure. Now, within this context, our goal is to design information campaigns which are the most effective. That is, choosing how many people and who to treat, taking into account three main facts. First, spillovers among farmers in the same village may occur, and this has been previously documented. Second, treatment can be costly, which means that treating each individual can be suboptimal. And third, network data, while relevant for the design of the treatment assignment, can often be difficult or infeasible to collect in practice. Now, within this context, there are two main research questions that I try to tackle. The first is whether we can test whether what the policymaker is currently doing is optimal, that is, maximize benefits net of cost, and whether we can conduct inference on this hypothesis. The second question is whether we can provide a measure which indicates the direction for a welfare improvement to the policymaker and ultimately estimate the best policy. And you can think about many other examples which follow within this category, such as cash transfer program, health and welfare programs, and so on. Now, the paper that I'm presenting studies the problem of allocating treatment to maximize the average outcome in the population, that I will denote as welfare, taking spillovers into account. So let me start from a very basic example, just to illustrate the main intuition behind the approach. Now, in this example, I have no cost. I have a very simple policy, just choosing how many people to treat, and a simple model where script ni denotes the friend of individual I. Now, let me denote yi to be the outcome of interest, and di to be a binary treatment assignment, either 0 or 1. Now, let me say that yi is equal to di times gamma 1, where gamma 1 denotes the direct effect of the treatment. Now, again, just for illustrative purposes, in this simple example, let me say that yi depends on the share of treated friends as well, which captures some measure of spillovers. Now, in this simple example, the best policy will be to treat everybody whenever the sum of the coefficient, gamma 1 plus gamma 2, is positive. In practice, in economics, we may expect some decrease in marginal return, so the more and more friends are treated, the larger may be the effect, which makes the design of the policy unclear, especially once we incorporate also the cost of the treatment inside the equation. So again, when we talk about policy, we need to take into account the policy space that we want to consider. And so as a policy space, let me just consider the simplest possible policy, which is choosing how many people to treat. That is the probability that the I is equal to 1, which I denote with beta. Now, if this is the policy of interest, welfare denotes the average expectation of the outcome, where the average is taken with respect to the treatment assignment beta, and the welfare maximizing policy is just the maximizer of such expectation. Now, in practice, you may consider more complex policies. So for instance, you may want to target treatments differently based on observable characteristics. Or for instance, you may want to incorporate constraints on the policy space. And these are things that I can allow in the framework and which are discussed in the paper. But I won't discuss throughout most of this presentation just for illustrative purposes. That is, for simplicity, I'm going to just look at a policy, which is choosing how many people to treat. Now, let me try to convey the basic intuition behind the approach. As I was mentioning before, network data is often difficult to collect. And so the approach that I take works as follows. Let's consider that we have a couple of regions, say 2 regions in this example. And we have a few unobserved, and the network within each region is unobserved to the researcher. Now, what we can observe are the treatment assignments. That is here denoted with different colors. Let's suppose that the policymaker is currently treating, say, 30% of the people. So what we can do is that we can treat 30% of the people in a given region, treat a little bit more in the other region, say 35% in the other region, which will allow us to estimate the marginal effect around 33%. Now, what we can do is that we can test whether the slope of welfare around 33% is equal to 0. And if we can reject the null hypothesis that such a slope is equal to 0, we can recommend to the policymaker to run a larger scale experiment, and at the same time also recommend to the policymaker how to improve current decision by looking at the sign of the slope. Of course, we will need to choose appropriately the difference in treatment probability, as I will discuss later during the presentation. Now, let me give you an overview and contribution. So approximately 40% of experimental paper in 2020 published in the top 5 econ journal at least mention spillover effects as a possible threat for estimating the effect of the program. However, standard experiments with spillover effect are geared towards the estimation of treatment effects, such as treating everybody in a region versus treating nobody. And this is not quite sufficient for welfare maximization. So what this paper does is the following. First, I design a short or single wave experiment where I randomize treatment and collect outcomes only once, which identifies policy relevant estimate, that is, identify a direction for a welfare improvement, but it also allows for inference on treatment and spillover effects, which can be of independent interest. Now, as a second contribution, I design a multi-wave experiment or sequential experiment, which efficiently recovers the best policy, but also improves participants' welfare. Now, to be a little bit more concrete, and I'm going to dig into the math a little bit later, the multi-wave experiment, what it does is that it controls the in-sample and out-of-sample regret at a fast rate in the number of iterations T and the number of cluster K. That is, if we look at the difference between the welfare evaluated at the best policy beta star and the welfare evaluated at the estimated policy beta hets, this difference converges to 0 at a rate which is 1 over K, where K is the number of clusters. And if I look at the in-sample regret, that is the regret on the participants, such rate will converge to 0 at a rate log K over K, so approximately 1 over K, up to a logarithmic factor. Now, this is quite fast, as we may expect alternatively rates, which are of order 1 of square root rate, which implies that if I want to control the error up to 1%, I only need 100 clusters instead of, say, 10,000 clusters. So the framework that I present is the first, which studies experimental design to maximize welfare with unobserved or unknown spillovers, and I also have some related work in the presence of observed spillovers. Now let me connect to the literature. So I connect to the literature on experimental design, which studies inference in the context of interference, inference on treatment effects, which, as I was mentioning before, is not quite sufficient for policy design. And there is some related literature on optimization, such as some work on pricing in two-sided markets, bandits with IID data, or adaptive randomization in the absence of interference. Now, none of these problems study the problem of policy design where I have spillovers on a network or partial interference, that is, interference which does not occur between clusters, and the goal is to design the best policy. Now, there is also some other literature which studies the problem of inference on networks and clusters. And here the main distinction is that here what I study is policy and experimental design instead of inference on treatment effects. And finally, there are other literature which I connect to more broadly, which is the literature on statistical treatment choice. We study the problem of choosing whom to treat, but in the context where you have data from an existing experiment or observational study, instead of running your own experiment. There is some literature on seeding and centrality measure, which leverage specific models, such as diffusion mechanism, to find what are the most central individual, as opposed to the framework which I study, which leverage adaptivity in the context, in a causal inference type of potential outcome framework context. There is some literature on peer and groups allocation, which is quite different from the problem of giving treatments in the context that I study. And then I relate to the literature on optimal taxation for the focus on the marginal effect. Now, none of these studies the problem of experimental design or adaptive assignments, which I study in the current paper. So the paper that I'm going to present lies at the intersection of three main research agendas that I have. One is on experimental design, the other is on policy design and decision-making, and the other is on inference on quasi-experiments. Now, the paper that I present relates, with some differences, which I will explain towards the end of the talk, with some other works that I have. So for instance, I have some work on experimental design under interference, where the goal is precise inference on treatment effects, where I do observe the network. I have some works in the context of policy design and decision-making, where I don't run an experiment, and instead I have an existing experiment. And then I have some other related work, which do not really relate to the problem that I'm presenting, but relate to the research agenda per se. Now, I take this as a pause to take questions.
We do not have questions in the chat as of now. Again, I will remind, if you have a question, please send it to the chat, and then I will unmute you at the next pause. I wonder if our panelists have any questions.
Maybe just one clarification question. So the Davide, in your simple example, that looks like you are assuming like homogeneous treatment effects. Maybe heterogeneity is only through this number of neighbors, but is your framework kind of, to what extent you are allowing heterogeneous effects?
Right, that's a very good question. I'm going to present the explicit model later on, but what I allow is that you may have heterogeneity also in the neighbor's identity, which means that the outcome model can also depend on who are my neighbors itself. So there can be some heterogeneity. The heterogeneity which is not allowed in the framework that I present is between clusters. That is, once you take the expectation across also the distribution of who are my friends, these expectations are going to be homogeneous across clusters. But I do have extension where I also have heterogeneity in the cluster identity itself. So you can think in two dimensions. The first is the individual level identity or neighbor's identity, and this is allowed in the framework. And then the cluster identity, I'm not going to discuss it during this talk, but towards the end, I'm going to discuss it as a part of the extensions.
Thank you.
But I'm going to be more clear in a couple of slides, and then if any other question arises, please let me know. Yeah.
Oh, I wanted to ask. Sorry, I don't know if you can hear. You can hear me. I wanted to ask about from an experimental design perspective, what's the role of the K and T, right? So K is the number of villages, and T is the number of periods. So I guess from an experimental's perspective, there is some trade-off or balance that they would like to think of these two.
Right. So basically here, what I'm going to do is that the framework that I study, first of all, fix the number of clusters. So the guarantees are for a finite number of clusters, which means that for any K in the context of the adaptive experiment. And the idea is to fix in the number of clusters because you incorporate this idea that you have limited information about the network, which really means that you can partition the network only into a finite number of components and not infinitely many. Now, with respect to the number of iterations, what I do is that I assume that the number of clusters is going to be proportional 2 times the number of iterations to obtain such guarantees. And the trade-off that you were discussing actually occur not really in terms of K and T, but with respect to the size of the cluster. That is, there is some trade-off in the sense of how many people do I sample from each cluster, with respect also to the number of clusters and iterations that I have in mind. So this is really a type of trade-off that occurs here, but what I'm going to consider is I have a finite number of clusters, so fixed K, and then N is going to be large. So the size of the cluster itself, and the sample from each cluster is going to be sufficiently large.
Thank you.
So Okay, so please interrupt me if I freeze or anything happens, because I have this fear, so please let me know. Yeah. All right, let me discuss the single wave experiment first. So the basic setup works as follows. Individuals are organized in relatively few large clusters with capital N units. And within each cluster, individuals interact with at most gamma and many others. So you can think about a cluster to be a region, and then individuals may interact with farmers in the same village or farmers in nearby villages, but not with farmers which are far apart in the same region. Each cluster may have different realized network, but the distribution is going to be drawn from the network is going to be drawn from a same distribution. I'm going to be clear in a second. And outcomes depend arbitrarily on neighbors assignment. Now, to visualize a little bit the problem, the setup works as follows. We have some treatment assignment, D for individual I in cluster K, which may be assigned based on covariate, X for individual I in cluster K, based on some assignment rule which we're going to design. And now what we do observe is not the network, but instead are possibly the covariates and the treatment assignment, the nodes with different colors here. Now we also sample the post-treatment outcome, that is the outcome for individual I in cluster K post-treatment, pre-treatment, yi0k, treatment assignment and the covariates for small n unit in capital K clusters. Now, eventually, we're going to go to a target population where the only thing that we observe are the covariates. And so we're going to use the estimated policy to target individuals based on these observable characteristics. Now, for the moment, consider one wave experiment, so t is equal to 1, and one single cluster for simplicity. And let's assume that there are no covariates. This is discussed in the paper, but for simplicity, let's forget about covariates, and just let's consider treatment probabilities. Now, the network formation model that I have in mind works as follows. The connection between I and J in cluster K is some function f, which may depend on unobservable of individual I, unobservable of individual J in cluster K. But then at the same time, I and J in cluster K may not connect if they are too far apart. That is, I can only connect with gamma and many other units, which is captured by the sum of such indicators. So we can think about farmers in a given region can only interact with the same or nearby villages. And the outcome of interest that I have in mind for in cluster K is some unknown function R, which depends on my own treatment assignment, the treatment assignment of my friends. So here there is no functional assumption on the treatment assignment of my friends. So you may have some heterogeneity on those. Some unobservable of myself and my friends, and also the identity of my friends, plus some observable characteristic nu I1, which are exogenous. There is also some cluster fixed effect. When we will have time is also a separable time fixed effect is also allowed. And then we have some baseline outcome yi0. Now we can write in cluster K, where these nu I are IID exogenous and observable for simplicity, that the expectation of the outcome conditional on my own treatment assignment is some simple function which only depends on my own treatment assignment and the treatment probability beta of my friends, plus some cluster fixed effect. Now we can define welfare to be the expectation of the outcome net of the cost of the treatment C times the probability of treatment, the marginal effect to be the derivative of welfare, and the direct effect of the treatment to be the difference between me being treated and me not being treated, fixing the treatment probability of my friends. Now here, V of beta, that is the marginal effect, also captures spillovers, in the sense that it is a function of the direct effect of the treatment, but also the marginal spillover effect, that is the marginal effect of increasing the treatment probability of my friends. And it provides a direction for an improvement, that is positive marginal effect will tell us that we should increase current policy, but it also allows us to test whether certain policy are the best policy, assuming that the best policy is in the interior. So to convey the main intuition, let's suppose that we are currently treating 33% of the people. We take a couple of clusters, and instead of treating 33% of the people, which in this case would not allow us to identify the marginal effect, but only the direct effect of the treatment, we say, well, let's treat a little bit more in a cluster, a little bit less in another cluster, so that we can identify the marginal effect of the treatment. So to be a little bit more specific, suppose that we want to estimate the marginal effect. The experiment works as follows. We take a bunch of clusters, say 6 clusters, and we're going to pair these clusters. So we're going to construct 3 pairs of clusters. Now, within each pair, for each cluster, we're going to choose a cluster-specific treatment probability beta k, where beta k is beta plus something small, eta n, or beta minus something small for each element in a pair. We then estimate the marginal effect using a simple difference in difference. That is, we take the post-treatment outcome, average over cluster k+1, we subtract the pre-treatment outcome, average over cluster k+1, and then we subtract the difference from the other element in the pair, and we rescale by 1/2 times the small number eta n, which we will choose. So let me try to convey the main intuition, which is very simple, of how we can identify the marginal effect here. So in the first period, at the baseline period, what we can identify is the difference in the fixed effect between two clusters, cluster 2 and cluster 1. Now let's go in the first period where we actually run the experiment. We got two clusters, say here denoted with different colors. And for a cluster, what we can identify is the welfare evaluated at the treatment probability beta minus something small plus some cluster fixed effects, and the welfare evaluated at beta plus something small plus some cluster fixed effect. Now, if we take the difference, this is approximately equal to 2 times the derivative times eta plus the difference in fixed effect. And so a difference in difference will allow us to estimate the marginal effect consistently. That is, if we look at the difference between the estimated marginal effect and the marginal effect evaluated at the treatment probability beta of interest, this difference will converge to 0 at a rate which depends on two components. The first component captures the bias, and which depends on the deviation parameter eta n. So the larger eta n, the larger the bias, but the smaller the variance. Now the variance itself will depend eta n inversively, and then it will also depend on how many people I can connect with, gamma n, that is the maximum degree. Intuitively, if everybody can connect with everybody else arbitrarily in a given cluster, then we cannot really control the variance, and we cannot really have concentration of the estimated marginal effect. Now, this bound will provide us with a trade-off for choosing the Turing parameter, and you can find a rule of thumb in the paper, in the appendix of the paper. Now, in the paper, I provide a series of results. So, for instance, I characterize the asymptotic distribution of the estimated marginal effect appropriately rescaled. I also construct a test statistic, which will allow us to test whether the marginal effect is equal to 0 using clusters pair and using a finite number of clusters, say 8 clusters, 10 clusters, and so on. And here, the finite cluster asymptotics are possible because of this pairing design. Now, I also provide guarantees to estimate the marginal effect of increasing the treatment probability of my friend Solly, and also the direct effect of the treatment. That is the effect of me being treated versus me not being treated, fixing the treatment probability of my friends. Now, for instance, if we look at the expectation of the estimated direct effect of the treatment, pulled across all the clusters, this expectation will be equal to the target estimate plus a bias, which is asymptotically negligible, that is, which is of order faster than n to the power of -1/2. And I also provide guarantees to estimate the marginal spillover effect, as discussed before. Now, to visualize a little bit more the problem that I just tackled for practical implication, let me say that in practice, what people do in general is the following. They say, let's take a couple of clusters, and let's say that we randomize this couple of clusters at a given saturation probability. For instance, 75%. Now, let's take two other clusters, and let's choose a treatment probability 0%. Now, what we can identify in this setup, which often people use in practice, is the direct effect of the treatment at 75%, but also the effect of me being treated, or 75% of the people being treated versus none of the people being treated, by pooling cluster at 75% and 0%. That is, by using all the observations that we can at 75% and 0%. Now, what I say, well, let's do a very small change to the original experiment. That is, let's induce a small perturbation around 75% and around 0%. And let's still keep pooling observation now, not exactly at 75%, but around 75% and around 0%. Now, what we can again estimate consistently is the direct effect and the effect of being treated at 75% or 0%, up to a bias which now occurs, but is asymptotically negligible. That is, we don't lose anything in terms of the set of estimates that we can recover. At the same time, though, we can also estimate the marginal effect, which is useful for decision making, and the marginal spillover effect, that is the marginal effect of increasing the treatment probability around 75% and 0%. That is the class of estimate that you can estimate increases without much any cost in terms of the original estimate that you were estimating before. So I want to pause here for questions.
It doesn't seem that we have anything in the chat. I will ask panelists again if they want to ask something.
Oh, I wanted to ask, so I can see for scalar beta, I mean, you can just perturb it by beta plus some small number and beta minus some small number. But what if it's vector valued? So then this perturbation will only give you a direction, right?
That's correct. So basically what you can do, there are two approaches in the setting. You can still test one single direction to be equal to 0. So this is still a valid null hypothesis that you can test for optimality of the policy, because you may not be optimal. So you should test whether it's equal to 0 across all directions. So it's sufficient to test only one direction. But in the paper, actually, I study how you can also test across multiple directions. And so what you should do there is that you should allocate different packets of clusters to different directions that you want to estimate, and then use different pairs of clusters to estimate such direction. So what this means really is that, of course, you have a trade-off in terms of how many directions you want to test being equal to 0 with respect to power of each test. And so in this context, what you may want to do is basically to choose it appropriately the number of directions. You may not want to test all the directions because this may be too many, but you want to test sufficiently enough to be sufficiently powered. So there is some trade-off there, and I do discuss how you can do it, but the idea is that you basically allocate different packets of clusters within each direction.
Maybe that's a stupid question, but I have one. It seems that if you're trying to change beta slightly, you really run into restriction that K has to be very large, because if K kind of medium size, different betas would not really produce much of a variation in the number of treated guys.
So rather, K is still finite, so K is fixed, more like N, the sample size needs to be sufficiently large.
Okay.
So if eta gets smaller and smaller, then N should be larger and larger. And in
Right.
fact, in the rule of thumb, there is an inverse relationship between N and the sample size. So eta, this should depend on the sample size itself. Yeah.
Okay.
K can be fixed. Of course, the more cluster, the better it is. But really here is in N in terms of the sample size. And the reason why K is fixed in this framework is because it incorporates this idea that you don't have much information about the network, which means that you can partition the network only into a few components, which you actually believe are independent.
And all clusters has to be roughly the same size?
So here I'm assuming that N is the same across clusters, but really what you need is that the size of the cluster is proportional to each other.
Thank you. I think you can. Oh, Toru, you want to ask?
Sorry, may I just one quick question? So in your
Yeah.
choice of eta, you assume kind of like a deterministic way of choosing eta, or maybe is there any gain of randomizing choice of eta?
That's a very good question. So I haven't thought about that. My answer so far is deterministic, but that's a very good question. I haven't thought about this. Yeah, I have to think more carefully. So basically in the rule of thumb, I say, well, you can choose eta based on, you can basically have some approximation of the curvature, and then you can use this approximated curvature, which may be a good guess to choose eta together with the sample size. But you're right that maybe a randomized eta may also work. The important thing is that the sign is not randomized within each pair. So one element is negative, the other is positive. But then that's a good question. Yeah, thank you.
We can move forward. Yeah.
All right, so let's suppose that we're not at the optimum, so we run an adaptive experiment. So how do we estimate beta star with a sequential experiment? So here what we do is that we are going to randomize treatment and outcomes sequentially. That is, we collect outcomes YIT in each period and treatment assignment DIT in each period. And the experiment works as follows. We're going to initialize the beta across all the clusters at the same starting value, beta 0. So same initialization. We're going to take our packets of clusters, say 6 clusters. We're going to pair our cluster into 3 pairs. And now we're going to construct a circle for which the first cluster is connected to the second cluster, which is connected to the third cluster, connected back to the first cluster. Now, what we do is that we use policy update in the spirit of gradient descent. That is, we're going to update our policy beta and cluster k at time t based on the previous policy, plus some learning rate, alpha kt, times the estimated marginal effect, v hat. Now, the estimated marginal effect that we're going to use is not the one obtained from the same pair of clusters, but in fact, it's the marginal effect estimated from a different pair, from the consecutive pair of clusters. And I'm going to explain why in a second. Within each pair, we're going to use this small randomization that I just discussed before, where beta kt is plus minus this small eta n. Now, if we choose k to be twice as large as the number of iterations, under regularity condition, we obtain the worst case welfare loss, that is different between the welfare evaluated at beta star and the welfare evaluated at the policy that we deploy in the experiment, worst case across all the cluster, will converge to zero at a rate which is log t over t, where t is the number of iterations. So going back to our own question also before, p here is the dimension of the parameter space. So here p is playing a role in terms that the regret will depend on p as well, polynomially. The auto-sample regret is also controlled at a rate which is 1 over t. Now here the rate 1 over k occurs because we can choose k as we want. So we're going to choose the smallest k we can, k is equal to 2 times the number of iterations, and obtain the rate 1 over k. Now for n, which is sufficiently large, that is n grows exponentially with the number of iterations, or alternatively, the number of iterations grows logarithmically with n, that is t is very small, we can actually obtain faster rate of the auto-sample regret, which are exponential in the number of iterations. Now this is stronger than what you would obtain with cluster as sample units. If you were to use just cluster as sample units, you may incur in a series of problems. One is a course of dimensionality, that is a dependence of p which is exponential, but more importantly is that the rate of conversion will be expected to be 1 over square root k, which means that if you want to control the error, say at 1%, instead of 10,000 clusters, you only need 100, as I was mentioning before. Now, on the derivation uses some recursive concentration, which I need to leverage within each pair for local dependency graph, and it leverages a concavity assumption. And one important role is played by the circular procedure, where the circular procedure allows me to control the bias which would otherwise occur due to repeated sampling and dependence. So why am I updating the policy in a given pair of clusters using the gradient estimated from the consecutive pair of clusters? Let me try to convey the main intuition through this simple graph. Now, in this graph, I consider the following model. I have some unobservable, nu it minus 1, which are serially correlated. So nu it minus 1 may affect nu it. Now, at the same time, my outcomes may depend on such unobservable. And the way I design the experiment, say, is through repeated sampling. That is, I'm not using the procedure that I just proposed before, where I use this circular approach. Now, if I were to use this repeated sampling, what this would imply is that the policy in cluster k at time t may depend on the outcome in the previous period in the same cluster k. And the policy beta kt may affect my treatment assignment in the consecutive period, which itself affects my outcome, and so on. Now, the implication is that if I look at the expectation average with respect to the distribution where beta kt is the treatment probability, well, this expectation of my outcome at time t in cluster k will be different than my conditional expectation, where I condition on my parameter beta kt. Now, why this difference matters? Well, this difference matters because ultimately we may want to go on a new population and implement our beta star in a new population where this beta star will stay there, which means that my beta star will affect my outcome at time t minus 1, but also my outcome at time t. And the effect through t minus 1 is, of course, through treatment assignment here omitted in the picture. So what this implies is that this will induce a bias in the estimation of the marginal effect, which we want to avoid. So the circular procedure works as follows. So we are in the first pair of clusters, and we say, OK, now for the first pair of clusters, at time t is equal to 2, we use information from the second pair. Now, since we are using information from the second pair, the estimated marginal effect is independent of my outcome for the first pair. Now, what happens at time t is equal to 3? Now, at time t is equal to 3, I'm still using information for the first pair of clusters, using the estimated marginal effect from the second pair of clusters. Now, the policy in the second pair of clusters was updated using information from the third pair of clusters, which implies that the first pair depends on the third pair at this point by t is equal to 3. So any sample splitting or cross-fitting procedure in this setup with this sequential nature with clustered repeated sampling will fail in our context. The circular approach allows us to maximize the number of clusters that we can use relative to the number of iterations, not to incur the bias that I just described. Now, one question of interest that we may ask is the following. So far, the policy that you presented is a policy that uses very limited information. And in fact, it only uses information from, say, covariates of individuals and nothing more. So it doesn't use any information about the network. So there is some sense, can we give some comparison of what we would observe if we were to use information from the network compared to the policy where we don't? So in this type of comparison, I'm going to make more restrictive assumption with the goal of providing one comparison and opening new research questions for future directions. So what I'm studying here is the largest welfare when the network is observed, which I take where I take the expectation where I can choose any arbitrary distribution, joint distribution on the treatment assignment, which may depend on the network structure and the covariates of everybody else. And I compare it to the welfare at the best policy where I don't observe such a network. Now I make additional assumptions to obtain some results in this context. The first assumption is that costs are the opportunity cost without spillover effects, and I'm going to be explicit in a second about this. The second assumption is that individuals depend on the share of treated friends, and you may have some heterogeneity in covariates which though are observables. Now, what about the first assumption? The first assumption is saying the following. Suppose that we have a stock of treatments, and we can choose whether to randomize the stock of treatment to people in the same or nearby villages, or to randomize the stock of treatment to people which are spread out on a large population, much larger than the number of treatment that we can assign. Now, in the second case, what we would observe is only the direct effect of the treatment, and we will not generate spillover, assuming that the number of treatments is much smaller, of order of magnitude much smaller than the overall population, such as, say, the entire US country. Now, in the second case, the opportunity cost of our intervention is the direct effect that we would generate if there were no spillovers, that if we were to randomize treatment in the absence of spillover effects. Now, if this is the cost of the treatment, that is the cost of an intervention where there are no spillover effects, then we can show that under regularity condition, this difference between the welfare where we do observe the network and the welfare where we don't converges to zero as the size of the network increases. So in this context, there is no need to collect network information. Of course, there are open questions of what happens if we are in the middle, that is where the costs are not exactly characterized by this difference by this direct effect, but by something else, which will allow us to characterize the relative cost and benefit of collecting the network, which is left for future research. Now, I want to pause here to take any question that may occur.
Yes, chat is still empty, and I will ask panelists again. If you have any questions, so we can move.
Let me just maybe, yeah. So in your procedure, so there's this updated step, which actually has this alpha. I think that's kind of determining
the learning rate.
Right. I just wonder if you have what we should know about the choice of alpha, or what's the right choice of alpha here?
Yeah, definitely. That's a very, very good question. So the choice of alpha here, I have some explicit suggestion for the choice of alpha. So my suggestion in practice, so let me go to the alpha here. Right, so this alpha KT plays a role. So my suggestion in practice here is to use alpha, which uses a gradient normal scaling. That is, alpha is equal to 1 over the norm of our gradient, which basically provides some information about the sign, and then some small number, say 10%. And I see that this works well in practice because combined with the circular procedure, basically it permits to control very large deviation which may occur in some pair of clusters, but not others. Now in practice, the choice of alpha also is important from theoretical results that you may obtain. So if you choose alpha adaptively, so alpha is, for instance, of order 1 over 10, or 1 over t, then you obtain the in-sample regret bounds. But if you choose alpha as I just described, where you have also this gradient normal scaling, you can obtain regret bounds without imposing a concavity, but instead only imposing strict quasi-concavity. So there is some trade-off in the type of assumption that you want to make and the choice of alpha that you want to make as well. So this is also discussed in the paper. Yeah, but in practice, I recommend to rescale by the norm and choose some small numbers, say 10%. That will work. Yeah. Any other question?
So I wanted to ask about about the rates and about how you can have different adaptive experiments. So one thing that's happening here is you have a fixed K, right? And each period, it's the same set of clusters or villages that you apply the experiment on. That's slightly different from a fully adaptive, like a bandit sort of experiment where you first take one cluster, then you use then you get the next cluster and so on. And I was wondering, I had two questions. One question was, would your rate results change if you're in this sort of in this adaptive experiment? And the second question I had was, which is in your, basically what the number of experiments is in your setup is K times T, right? Because in each time period, you run like experiments on K different cluster pairs. So I was a bit interested. I thought it was interesting that in your rate, it only depends on T and not maybe K times T, if that makes sense.
Right. These are all very good questions. So I have an extension in the paper which talks about this setup that you just described, in which you do sequentially you take a pair, then you estimate, then you take the consecutive pairs, and then you estimate. And this is relevant if you have staggered adoption, so you can only get treated once, such as most of the cases for vaccination. So in that case, you cannot control the worst case regret across clusters. So doing all together allow us to control regret, which is worst case across clusters. So it's max. So it's not average across the cluster itself. If you said you were to doing this, use a pair, then use the consecutive pair, etc., you would have for some clusters that incur a large loss and some other not, this average out, and so you can still control the regret, but it's not worst case across the cluster. So there is a trade-off also in terms of theoretical guarantees. And you care about the worst case regret across the clusters if you care, intuitively, if you care equally to different locations. So suppose that you're running an experiment in LA and in New York, you really don't want to say, yes, start from LA and then go to New York because New York is going to be better, but I want to control it worst case across LA and New York. So this is the main intuition why you want to look at this type of regret, but you can obtain weaker notion of regret if you were to do this type of rollout. So this is the first question. The second question on KT, yes. So in that case, the reason occurs because of this repeated sampling bias, which otherwise would occur. So because basically of this repeated sampling, what you need to do is that you need to update the policy using the estimated gradient from the consecutive policy, which means that you cannot really learn. It's like you need to update the cluster based on the consecutive policy, and the learning really occur from the number of iterations. So there is it's not that you're considering different policies across clusters, but you have the same starting value across the different clusters, which implies that the learning occurs through T, but not through K. And so this is why the regret is 1 over T or 1 over K, not 1 over T times K. So that's the idea. You cannot go in both. You cannot learn information in both dimensions as K and T grow. You can only learn information as either T or K or both grow, but only one direction. So this is the idea. Yeah. Any other question?
No, we should move.
Yeah. All right. So I'm going to give you a brief glimpse into some numerical studies. So in the numerical study, I consider a quadratic model in spillover effects, which is unknown in the experiment, and the parameters and standard deviation are calibrated to existing experiment on information diffusion and cache transfer programs. In this existing experiment, we do observe the network in practice, so we can calibrate the experiment to observe the network, but then in the simulation, I assume that the researcher does not know anything about the network other than the cluster structure. And so what I'm going to do is that I'm going to test the null hypothesis of whether I should increase treatment probability, running from a small treatment probability 10% up to the optimum, which is around 60%. And then I'm also going to run a multi-wave experiment. So in the first picture, what I report are two different plots. In the left-hand side plot, I report the power of the test. And so as we can see, the power increases as the number of clusters increases. And as the number of clusters oscillates between 20, 30, and 40, then the increase in power occurs, but it's not that large. But there is a substantial gain if we go from 10 to 20 clusters. Now, on the x-axis, what I'm reporting is the regret, which is the distance, basically, from the optimum. Now, what's interesting here is that what we could do is that we can try to do a power analysis in the context of welfare maximization. Now, in the context of welfare maximization, we don't really care about the power, but instead we care about what would be the welfare gain if we were to reject the null hypothesis of interest. In this example, what is the welfare gain if we were to reject the null hypothesis that we should not increase treatment probability? And if we do, we are going to increase treatment probability by a small amount, say 5%. Now, we can study what is the relative welfare improvement. And what we do observe in the right-hand side plot is that, again, there are some improvement in terms of relative welfare gain, going from 10 to, say, 20, 30, 40 clusters, but this improvement seems a little bit smaller. Now, why is that the case? Well, the reason is because lots of observations are needed to reject the null hypothesis that we are not at the optimum, as we are close to the optimum, but not exactly at the optimum. And so this is what the power plot is reporting. However, if we are already close to the optimum, there is no really need to reject the null hypothesis because, sure, there might be some improvement, but these improvements are going to be relatively small. And so this is what we observe in the right-hand side plot. And so this figure, what it's trying to report is that if researchers care about welfare, the way they should run power analysis in the first place is a little bit different, because they should take into account also the decision that they make upon rejection of the null hypothesis. Now, in the second plot, what I do is that I compare welfare out of sample and in sample with respect to the method that is going to use a simple grid search procedure. And I provide formal theoretical results and comparison also in the appendix, where I show that the proposed adaptive procedure outperform. Now, we do see so also in numerical studies. So in numerical studies, what we observe is that out of sample, outperformance oscillate between 2 percentage points, if I care about targeting information, up to 100 to 150 percentage points as the number of iteration increases, again for information, and I look at the in-sample regret. That is the regret on the participants. Now, if I look at the out-of-sample regret, the cache transfer program provides us larger gains, up to 60 percentage points, between 40 percentage points, but smaller gains for in-sample regret. That is, there is some trade-off between out-of-sample and in-sample. For some application, we have larger out-of-sample improvement, but smaller in-sample, and vice versa, but we still see improvements. Now, what I also do in the paper, and I'm going to skip the details just for sake of brevity, is that I also run an experiment on Amazon and Turk, where I try to incentivize people to take up COVID vaccines. And this was run in February 2020, so before the vaccination campaign was deployed. And in this experiment, what I do is that I calibrate to the result that I obtained from the Amazon and Turk experiment that I just ran. And I also simulate spillover effect for different values of spillover effects, because I cannot observe the spillover in the experiments. And so in this calibrated simulation, again, what I do observe is that as we increase the size of the spillover relative to the direct effect, ranging from 10 to 30% with respect to the direct effect, we observe relative welfare gain, again, by running the single wave experiment and then rejecting the null hypothesis and making decision of treating more and more people. And at the same time, this welfare gain decreases as we get closer to the best policy. I can give you more details if you have any question about this. Now, what I'm currently running, this is in collaboration with Precision Development, is an NGO, and the Chicago Innovation Lab in particular, postdoc just threw there at the lab is a real-world experiment where we are actually implementing this procedure with 500,000 farmers for information about weather predictions. So I will briefly pause here for questions and then move to extensions and conclusions.
Yes, we do have one question in the chat. It is from Andres Sarkar, and I unmute him.
Thank you. Thank you. Maybe, I mean, the question relates, I missed the first 5 minutes and I didn't read the paper, but usually in treatment effects with network interference, there is a problem of violated stable unit treatment value assumption, SUTVA. Does this have any relevance for your analysis? You naturally use spillover effects and so on. Does this control for this?
Yeah, for sure. So this is formalized exactly in the outcome model equation. So in the outcome model, you can explicitly see that my outcome will also depend on the treatment assignment of my friends, so violating the SUTVA assumption. So that's a very good question. Definitely it's taken into account in the context of interference here.
Okay, thanks. Thank you.
Thank you.
We probably should move so you can finish roughly on time.
All right, so I'm going to touch on some extension-related works and then move to the conclusion. So in the context of the extension, you find many extensions in the paper. So for instance, there is an open question of what happens if you have heterogeneity across clusters. And I provide 2 extensions in the context of heterogeneity. One in the case where covariates are drawn from different distribution across clusters, and you do observe such covariates. In this case, what you would like to do is to match clusters based on estimated feature of the distribution of covariates. And I provide an exact characterization between the worst case bias that you would incur and the best matching, which is based on reproducing kernel libre space embeddings. And the second extension is where instead you have different cluster types which may affect the outcome equation, and you do observe such types, such as, for instance, rural or urban regions. And in that case, what you would like to do is to match based on types. Now, another question is what happens if you have dynamic treatment effects. So suppose that the treatment effect propagates in time, and how do you design the experiment in that context? So you have an extension in that case, and what you would like to do there is that you would like to estimate the marginal effect of increasing treatment probability today and yesterday as well, and use the estimated marginal effect to then approximate the value function that you would obtain by running dynamic treatments, basically. Now, in this context, the estimated marginal effect allow you to improve the rate of convergence, but there are really many open questions in this context. So one issue, for instance, is that you may have a course of dimensionality and such type of problems. Now, this connects back to Karun's question where treatment can only be assigned once. So this is also studied in the appendix. There is also a question of what happens if you have strict quasi-concavity, which may occur, for instance, if you have herd immunity. So herd immunity may kick in only if after a while, many people are treated, so not immediately. Another type of extension that you find in the paper. Now, some interesting future direction is what happens if the bounded degree actually, if there is no condition on the bounded degree, so the bounded degree, there is no maximum degree that grow at a slower rate than the sample size, but in fact, there can be some arbitrary dependence, but some sort of ergodicity type assumption. So in this case, what can we do? I hint how you can still manage things in this setting. But of course, this opens also all possible new questions of how you can manage arbitrary dependency network setting without looking at the degree itself. And another question is what happens if networks also depends on the treatment assignments. And some open questions that I want to leave also to the audience. So can we actually characterize the value of collecting network information in generic setup? So I provide a formal theory in the paper where I show asymptotic equivalence as the cost is the opportunity cost of an intervention with no spillover effects. But there is really an open question: what is the value and benefit of collecting network information in such a setting? Another question: what if there are multiple equilibria? So these also partially connect to not the SUTVA in terms of no interference assumption, but the assumption of consistency of potential outcomes. So in general, if you have multiple equilibria, you may have a set of functions which characterize the response of individuals based on such equilibria. And so there is a question of what happens in such context, which really belongs more to the literature of partial identification and so on. And then what if utilities are unobserved? Some related work that I have So I have some work on policy targeting under network interference. And here the policy is done using data from an experiment which has already been run. From the experiment, you do observe information about the friends of the individuals, but in the policy that you design may not necessarily depend on network information. I have also some work in the context of fairness. So far we just target the expectation of our outcome, but what if we care about fair assignments themselves? And what if we want to trade off efficiency with respect to fairness? And so there is some work also in this direction. And then I have some other work where the goal is actually variance optimal design. So what I propose is a novel framework which studies two-wave experiment in the context of networks. And what I show is that in the context of network, two-wave experiments are quite tricky, because the pilot study, using a pilot study may lead to a confounded experiment in the main experiment, and it leads to interesting trade-off for the characterization of the pilot study, which I provide in this other paper. So let me skip the following slide. And let me just give you a glimpse inside one of these three papers, which is the policy targeting under network interference paper, before concluding. So what you could do instead of running the experiment as I propose is to say, okay, let's suppose that we have no cluster whatsoever, but in fact we only have one single fully connected network, and there are some spillovers within this network, but we do observe the network in the experiment. Now what we could do in that setting is that we can try to estimate the conditional mean and the propensity score, and we can even do it non-parametrically using some machine learning tools. And what I do in the paper is I provide some estimation procedure which allow for this machine learning estimation in such a context. Now we can then maximize the estimated welfare, where we actually use information from the quasi-experiment itself and the conditional mean function. And what we can show now is that the regret will depend not on the number of clusters, because there are no clusters, but in fact it will depend on the size of the network. So if we look at the difference between the welfare evaluated at the best policy and the welfare evaluated at the estimated policy, this difference will depend on n, where n is the size of the network that you sample. And will converge to 0 at a rate 1 over square root n whenever the degree is bounded in the network. Now, if the degree is unbounded, the constancy bar will also depend on the maximum degree. So this will affect itself the regret bound. And there are a few challenges in this context. So one is, for instance, is that you cannot directly use existing tool, but you need to extend symmetrization arguments and bounds on the Rademacher complexity in the context of network spillovers. So I'm going to jump to the conclusion. So in this paper, I've introduced a statistical framework for estimation and inference for welfare maximizing policy. The framework allows for unobserved and partial interference. So unobserved because I don't know the interference structure in a given cluster, partial because there is independence between clusters. And the experiment consists of a match pair local and two-stage design. So why match pair? Well, because I'm going to have pairs of clusters. Why match? Well, because as I discussed in the extension, if you have heterogeneity in the type of cluster, you may want to match based on such heterogeneity. Local, because within each pair, I'm going to induce some local perturbation. And two-stage, because I first choose the treatment probability for each element in the pair, and then I'm going to randomize across individuals. I've discussed an adaptive experiment for policy choice. I provide asymptotic properties and regret bounds of the procedure. And finally, I illustrate the method in a calibrated simulation. So this is pretty much it. And you find more on my website as well.
Thank you so much. You are super disciplined. So it's exactly on 0, you finished. So I will ask if panelists want to ask something, and then I will unmute everyone to simplify the discussion.
Okay, so let me ask a couple of questions. So maybe this is more like a application specific, but so in your framework, you basically assume that once you implement treatments, you kind of immediately see the responses of the outcome at that level. But in the practice of economics or social science, or maybe type of example you're looking at, what kind of time scale we should kind of think about after implementing treatments and getting responses, and how many actually rounds of adaptive experiments we can actually run in reality? Do you have anything to say on that? That's a great question. So it depends on the type of application that you have in mind. So for example, the paper that I was discussing with co-authors, it's an information campaign
And in that paper, what they do is that they first run the information campaign, and then during the information, at the end of the information session, they ask you, do you want to buy or you don't want to buy insurance? So at that point, you already know. You have immediate result from the outcome, because it's going to be whether they buy or not after the information session. And another example like this is the experiment I was mentioning that we're trying to run with precision development. So in that case, what we do is that we randomize information to individuals, and then we can immediately observe, in this case, the scale is 1 month, whether individual will interact more with the NGO, which means that whether response rates increases. So in this type of application, the outcome is quite fast to observe it. There are, of course, applications where outcomes instead can be long-term outcomes, and so these are more challenging, such as, for instance, this is mostly related to problems of say, health-related program. And in this case, longer-term outcome poses more challenge, which really means that you can only run a few iterations instead of, say, 10 or 20. You can run 3 or 4, and that's it. In this case, the time is like 6 months or so on. So going back to the previous example with precision development, if you look about engagement, you really have 1 month's response. Instead, you look at the harvest, at the result from the harvest, then it's 6 months. So that really also depends on the outcome you care about. Yeah.
I see. And sorry, one more question is that so in your definition of welfare, so you sum up the welfare over clusters, but for instance, if the welfare, I mean, there's a flow of welfare at every time period. So, like for instance, in case of vaccinations, the effect of vaccinations, the welfare impact should be measured, let's say, at each month or at each year, and hence that means when we actually define the welfare, we should also sum up over time as well. So that means well, the first villages where the treatments are actually implemented, they have a flow of welfare over multiple time periods. So that when the definition of welfare, those who are treated in the early part of the experiment should be weighted differently from those actually who are treated in the later time periods. Does that kind of change of criterion?
Yeah, so you're saying that you have some sort of weights which depend on the iteration. So in the first period they care more, and then in the subsequent period they care less. Is this correct?
Yeah, that's right.
Yeah, right. Yeah, so this is relatively tricky because so here welfare is basically the effect that you observe by randomized treatment and then observing the outcomes. And of course, you can have weights between different individuals as long as you have this linearity type structure, then that's still fine. And again, welfare, like the idea is that clusters are treated contemporaneously. If instead you have some sort of dynamic in the way you care about welfare, then this is more related to, say, a dynamic type structure, because in this case, the best policy is not going to be a stationary policy, but instead it's going to be a path of policy, which depends on the dynamic and how much you care about the dynamics. So this is a little bit different in terms of the type of design and the class of design that you want to consider. It's more related to dynamic treatment effects. I have some extension in that context, but is not directly related to what I'm discussing, because welfare is just the expectation of the intervention that I do today.
Thanks. Yeah, thank you.
So I think what's interesting related to this from more a theoretical perspective is what if you look at the regret, and so here the regret is average over time. So you can think about this as caring with the same weight across every time periods. So the question is, can you provide some regret guarantees if instead of having this one weight, you just have different weights? And can you still obtain some regret bounds in that context? My guess is yes. I haven't derived it, but I think the framework may still be valid if you have some weights, but I don't know. So I don't want to make any promise there, but I should try to see what happens to the regret if you care in terms of weighted average. So you have some sort of discounting and stuff. Yeah. But I don't know. So my answer is I don't know that. Yeah.
Oh, so actually just on this. Oh, sorry, Anna, you can ask.
No. I'm saying that I'm allowing everyone to be unmuted, so we have an open discussion. If you want to ask a question, you just raise a hand, and it will be much easier. Yes, Karun, please.
Oh, I mean, I was just curious about. So if I'm interested in out of sample regrets, and does it mean that if I do like a sort of this fully adaptive design, like a bandit design, I would get, as opposed to yours where you have like K fixed clusters, would a fully adaptive bandit design give me lower regrets? In the sense that
no, I see. Mm-hmm.
I mean, in the sense
Please,
that
sorry.
it might be like K times T. Well, not really K, but I mean, because you don't have K in a fully randomized setting, but you need fewer clusters and time in general. Well, that's kind of what I'm thinking.
So yeah, I see your point. So yeah, that's also that's very good question. The thing is that the point is that you're still not gonna have 1/kt, and the reason is because again K is T in the setting that you're describing, because you basically have 2 new clusters, and what you're gonna gain with K is faster concentration around the marginal effect, which really means that you need smaller sample size from each cluster to achieve this same type of guarantees. So the larger K here will give you concentration for the marginal effect. So basically, yeah, you need smaller sample size in practice.
I see. So I guess so. Yeah, I mean, I agree that K and T. I mean, in what I'm thinking, K and T, K equals T. I mean, there's just a 1 every time period, right? So I guess you get the same rates, but you just save, instead of doing K units every time period, you just do 1. Is that how I should think about it?
Right. Yes, right. Exactly. It's basically you need the smaller sample size in that context.
That's right.
Definitely. But still, you have the 1/T rate. You cannot.
Right.
I mean, you can improve. You can get exponential rate, and that I also derive it in the paper. But of course, yeah. You need the n in sufficiently large. Please.
Sorry, yeah, no. I guess I was thinking the n, having n in there is a bit like having a batched bandit experiment, basically because you're averaging across a lot of units. That enables you to estimate better, I guess. And so the second question I had, and which is probably the case that, I mean, I was interested in the lower bounds. So for the reason that we know that in some bandit experiments, and I mean, this is not what we're doing, of course, there's also network interference, but in some in standard bandit experiments, gradient bandits can fail. I mean, don't always reach the lower bounds. And I wonder, whereas in your case, I was wondering whether it does reach the lower bound, or if you have any thoughts on this.
Oh, yeah, that's a very good question. So I don't have, so here, so there are different lower bounds based on different set of assumptions, of course. So for example, I have in mind Shamir 2013, then you have some sort of lower bound where they're 1/√T or something like that. So here I don't have results in terms that I don't have a result which tell you, well, I have a upper and lower bound which match to each other. So what I'm saying is that the rate of convergence that you get is either 1/T or can even be faster. So it can even be exponential. Nice. But there is this trade-off in the sample size in this context. But I'm not telling you, I know that this exponential rate is the best rate. Maybe you have exponential to the exponential. I'm not sure about that. Yeah. But also it's a little bit, in this context, it's a little bit understated. So yeah. Well, that's a very
I mean, so in that regard, the exponential rate does happen in bandits, right? In the sense that, I mean, if you look at out of sample regrets, which is more like Casey and Soutman or these kinds of papers where you don't look at the experiments, but you only look at outcomes afterward. There you get exponential rates for the regret.
Right. Yeah, exactly. But the thing here is that, so you can obtain exponential rates. So that's completely right.
That's right.
Here you also obtain this logarithmic growth of the in-sample regret as well, basically. Worst case across classes. So this is also,
Yes, we do have a question from the audience, Andrei.
Thanks again. Does this work also for different types of treatment, like continuous treatments, for example, or is it for binary treatments only?
Oh, no. I have a footnote. So originally,
Okay.
I had actually a more extensive part with continuous treatment, but I have a footnote with the continuous treatment. Yes, you can think in terms of continuous treatment if those are deterministic. So, for example, you just fix it's just a number that you choose. So you can think in terms of continuous treatment. It's not going to change much. I only have a short footnote, but things will go through. It's actually the derivation are actually simpler because you don't have to take into account also the randomization of the treatment assigned in that context. Yeah.
Thanks. And multiple treatments are probably covered with multiple waves, or is this option also considered?
Oh, multiple treatments. So these I haven't really. So here, what I'm considering is a class of policies, and then I look the best over this class. So I don't have. So basically, you don't have continuous. You don't have binary. You have discrete. I don't have anything on the paper about that. My guess is that it wouldn't change much, but I don't have anything in the paper about that. But yeah, I should think more about this. Yeah, but my guess is that it wouldn't change much, but I should think more. Yeah.
Thanks.
Any more questions from the audience? If there is no question, I guess we can show the last slide for today, which essentially is announcing that this is the last seminar of this academic year. We do have exciting plan for September and October. Already a number of seminars are scheduled. We do start very early. September 2nd will be the first seminar of the next year. It will be Anna Bukovsky